Well, hello everyone, and welcome to the 11th session of our U.S. Territories Water Operator Training Series. Today is our fourth and final webinar on the topic of disinfection, and today we will be going over chlorine disinfection math. My name is Michelle Olson, and I am a water utility trainer and specialist with the Southwest Environmental Finance Center. The Southwest Environmental Finance Center operates out of the University of New Mexico School of Engineering, and this training series is funded by the U.S. Environmental Protection Agency. Before we begin, I'll let you take a moment to locate your control bar, and we'll do just a quick review. So the button labeled audio on the far left is for muting and unmuting yourself. Make sure you remain muted during the webinar. You can unmute yourself if you want to ask questions or if you have something to contribute to the discussion. You can also use the chat function in the middle to ask questions. If you post anything in the chat, make sure you send it to everyone. Don't send anything directly to me, as I may not be able to check the chat as I'm presenting. And if you need to leave the training for any reason, go ahead and use that leave button on the far right of your screen. Our U.S. Territories Water Operator Training Series is 26 sessions total, 1 hour each, and the trainers will vary depending on the topic. So this is the schedule for 2025. We have 2 more drinking water sessions after today for this year, and then we're going to have 13 more sessions, I believe, to come in 2026. So our next session in 2 weeks will be on surface water treatment. We'll be going over coagulation, flocculation, and sedimentation, and that'll include chemistry, process controls, and operations. Recordings of our sessions and copies of the material are available on our website, and we'll be posting that link in the chat for you guys. So today we're going to be going over chlorine disinfection math related to solids concentration and chemical solutions. We'll go over specific gravity, and then we'll close off the day looking at feed rate. So I'll give you a quick overview of what each of these are, and then we'll be working through some math equations together related to each of these topics. So first, let's talk about solids concentration and chemical solutions. So understanding solids concentration and chemical solutions are important to ensure that the concentration of chlorine that's added to our drinking water is at a safe level to protect public health. So we want to make sure that we're adding enough chlorine to stop the growth of pathogenic microorganisms, those microorganisms that cause disease, while making sure that we don't overchlorinate, which can cause illness and can increase the formation of disinfection byproducts. So as operators, you have to carefully monitor and adjust chlorine levels to follow federal requirements to make sure that you're in compliance with safe drinking water quality standards. Let's start with a quick review of what a chemical solution is. So a chemical solution is a homogeneous mixture of at least 2 substances. We have one substance known as a solute that's dissolved in a medium, also known as a solvent. And when I say homogeneous, I mean that the solute and the solvent have combined on a molecular level to become a new substance. So for example, a chemical solution that many of us are probably familiar with is hypochlorite solution, or sodium hypochlorite. So this is made up of a solute, in this case hypochlorite salt, plus a solvent, which in this case is water. We take our solute, the hypochlorite salt, and we add it to the solvent, the water, and we mix them together until the salt is completely dissolved. Now we have our chemical solution, our hypochlorite solution. So this is either done by the manufacturer or it can be done by the utility, depending on what type of chlorine you use for your system. Solids concentration is the amount of dry chemical by weight mixed with an amount of water by volume used to make a chemical solution. So this is important because it tells us how strong our chemical solution is. 10 milligrams of hypochlorite salt added to 1 liter of water is going to be a weaker chemical solution than 20 milligrams of hypochlorite salt added to 1 liter of water. The units of solids concentration then are the weight of our solids in milligrams by the volume of our liquid in liters. to give us a unit of milligrams per liter. What are the ways that concentration can be expressed? Well, we just talked about milligrams per liter, which is weight of solids over volume of liquids. We can also talk about it in terms of parts per million, which represents the number of parts of a substance per 1 million parts of the total mixture. Milligrams per liter can also be expressed as parts per million. So if we were to add 10 milligrams of hypochlorite salt to 1 liter of water, the concentration can be expressed as 10 milligrams per liter or 10 parts per million. They mean the same thing. Finally, we have purity. So purity is the mass of the chemical in a sample divided by the mass of the sample times 100. And that's kind of complicated. You don't have to remember that. But do remember that a 1% solution is equal to 10,000 milligrams per liter, which is also equal to 10,000 parts per million. So that means a 10% sodium hypochlorite solution is 100,000 milligrams per liter, which is also 100,000 parts per million. All right, chlorine dosage. So chlorine dosage is the amount of chlorine added to the system. As with our solids concentration, it's a concentration represented as a weight over volume. And it can be expressed as either milligrams per liter or parts per million. So sometimes you'll see pounds per day or gallons per day. So pounds per day or gallons per day is actually not a dosage. Pounds per day is weight over time. Gallons per day is volume over time. So therefore, those are rates. And in this case, feed rates, not concentrations. How do we know how much chlorine dosage our system needs? Well, the dosage is the total amount of chlorine used through both demand plus the chlorine residual that we want left in our system after the demand is satisfied. So those together equal our dosage. Well, what is chlorine demand? Chlorine reacts with iron, manganese, organic matter, turbidity, and microorganisms in the water. The amount of chlorine that's used by those things is what we call the demand. It's the amount of chlorine that's consumed or bound up by those materials in the water, and it's expressed as milligrams per liter. So it's important to be aware that demand does change with time. Because it takes time for chlorine to disinfect, it's not an instant process, demand usually goes up with time to a certain extent, and then it levels off. So this type of chlorine is not available as a residual because it's what's being used. A chlorine residual is the amount of chlorine that remains in the system after the demand is satisfied. So like demand, residual also changes with time. In this case, the more time that passes after dosage, the lower the residual will be until all of the demand is satisfied. Chlorine residuals are important because this is the chlorine left in the water that's available for further disinfection. So chlorine residuals are what you measure and report on your backed each sample chains of custody each month. There are 3 types of chlorine residuals. The first is the free chlorine residual. Free chlorine is the amount of chlorine available to disinfect water, and it's the most effective form of chlorine to have in your system. We get combined chlorine when free chlorine combines with nitrogen compounds to form chloramines. And the total chlorine residual is the amount of free chlorine plus the amount of combined chlorine in the system. So total equals combined plus free. We can calculate the chlorine dosage we need to add to our system if we know the chlorine demand. That's the amount used for disinfection. And the residual we want, how much chlorine is left in the system. So dosage equals demand plus residual. We can also rearrange this equation to solve for the other 2 variables. If we know the dosage and we measure the residual, we can calculate how much chlorine is being used for demand. So demand equals dosage minus residual. And if we know the dosage and the demand, we can subtract the demand from the dosage to calculate our residual. So you should memorize this equation because it's not provided on the WPI formula sheet when you take your certification exam. All right, let's go over a problem together. So this problem is asking you to calculate chlorine dosage if the demand is 0.35 milligrams per liter and the residual is 0.82 milligrams per liter. You have the dosage equation and a list of possible answers. A is minus 0.47 milligrams per liter, B is 0.47 milligrams per liter, C is 1.17 milligrams per liter, and D is 2.34 milligrams per liter. All right, so to get started, we want to figure out what we are trying to solve for, what we're trying to calculate. And in this case, it's going to be chlorine dosage. Okay. Now let's look and see what our knowns are, what information we're given. So the first thing we're told is that the demand is 0.35 milligrams per liter, and the residual is 0.82 milligrams per liter. So the first thing we're going to do is we're going to set up the equation to solve for our unknown, which in this case is dosage. Well, if we look, the equation is already set up to calculate dosage, so we don't need to do any rearranging. We can move on to step 2. For step 2, we're going to make sure that our units match. So we're given demand in milligrams per liter, which matches what we want in the equation. And we have residual in milligrams per liter, which also matches the equation. So our units are good, so we can move on to step 3. Now we want to plug in the known values for demand and residual into our equation. So we're going to get dosage equals 0.35 milligrams per liter plus 0.82 milligrams per liter. And now we can solve it. So we get an answer of 1.17 milligrams per liter. So our chlorine dosage is 1.17 milligrams per liter. So our answer is C. All right, does anybody have any questions about how we got that? Okay, so let's move on to another question. So this problem instructs us to calculate the residual chlorine if the demand is 2.0 milligrams per liter and the dosage is 2.8 milligrams per liter. All right, so we're going to follow the same steps. The first thing we want to do is try to figure out what we are trying to calculate. So in this case, we want to calculate residual chlorine. Now let's look at the information that we're given. We're told that the demand is 2.0 milligrams per liter, and the dosage is 2.8 milligrams per liter. You know your dosage equation, so we have that. So let's move on to our first step. Step 1 is to set up the equation to solve for the unknown, which in this case is residual. Well, the equation is set up for us to find dosage. It says dosage equals demand plus residual. So we want to isolate residual in the equation. And the way that we're going to do that is we're going to move demand to the other side of the equation. If we subtract both sides of the equation by demand, they cancel each other out on the right side, and we are left with an equation that says residual equals dosage minus demand. Okay? So now we can move on to step 2. We want to make sure that our units match before we can solve anything. So we're given demand in milligrams per liter, which matches the equation, and we have dosage in milligrams per liter. So we're good to go. We can move on to step 3. And we're going to plug in our values for dosage and demand. So we get residual equals 2.8 milligrams per liter minus 2.0 milligrams per liter. We can solve, and we get an answer of 0.8 milligrams per liter. So our residual chlorine is going to be 0.8 milligrams per liter. All right, does anybody have any questions about this before I move on? Okay, so let's move on to specific gravity. We looked at solids concentration and what that tells us about the concentration of our chemical solutions. But what happens if our sodium hydroxide solution is getting old and we need to know the current concentration to make sure that we're dosing properly? Or what if we want to calculate something else? Like what if we need to know the weight of our solution? Well, we can use specific gravity to help with these things. Specific gravity is the ratio of the density of a substance to the density of a standard. And I'm expressing that ratio here as a fraction because that's going to be useful to us later. Because specific gravity is a ratio, it's a unitless number. The standards that we use are usually either water for a liquid or a solid and air for a gas. Water, since it's a standard, has a specific gravity of 1, meaning that water is equally as dense as itself. So another way to think about that is that any number divided by itself equals 1. If we're trying to calculate the specific gravity of a liquid and we're using water as our standard, we're calculating how much heavier or lighter than water our liquid is. So some liquids are lighter than water, like oil. Oil will float if combined with water, like in the picture of the salad dressing here that's separated. Water has a specific gravity of 1, so oil is going to be lighter, and it's going to have a specific gravity of less than 1. So like 0.8 to 0.9. Some liquids are heavier than water, and they'll sink. So think of honey, for example. If you add honey to a glass of water and don't mix it together, it's going to sink to the bottom of the glass. Chlorine solutions are heavier than water, so their specific gravities are going to be greater than 1. We can get specific gravity 2 different ways. The first way is we can measure specific gravity with a hydrometer. So a hydrometer looks like this. And I know it's a little small, it might be kind of hard to see, but it's got this bulb on the bottom and it has numbers on the side, and it kind of looks like a thermometer. So to measure specific gravity with a hydrometer, you need a container with the liquid that you're testing. And then you put the hydrometer inside the liquid and it should float. And you put it in and you kind of want to give it a spin to make sure it doesn't stick to any sides. And once it comes to a rest, then you're going to read the number on the hydrometer where the liquid intersects with the hydrometer, where the top of the liquid intersects. So that's going to be your specific gravity. Well, we can also calculate specific gravity of a solution. And in order to do that, we need to know its specific weight in pounds per gallon. So specific weight is how many pounds 1 gallon of our solution weighs. It's kind of like that riddle. What's heavier, a ton of feathers or a ton of bricks? Well, they both weigh the same, right? A ton. But that tricks us because we know intuitively that feathers are less dense than bricks. So if we compare them based on a standardized weight, a ton of feathers to a ton of bricks, their volumes are going to be very different. We're going to have a lot more feathers than bricks to get to a ton. But if we compare the same volume of each, we see that a gallon of feathers is lighter than a gallon of bricks. Therefore, the specific weight of feathers is going to be much smaller than the specific weight of bricks. So everything with a mass has a specific weight. Feathers, bricks, chlorine solution, even I have a specific weight. So we could calculate how many pounds a gallon of Michelle weighs. We just have to measure my volume and my weight. And it's important to understand specific weight because when we get to feed rate, it's going to help us convert between weight and volume. So going back to our equation, let's take the specific weight of our solution in pounds per gallon and divide that by 8.34 pounds per gallon. So does anybody know what 8.34 pounds per gallon is? Why we use that number? Well, it's the specific weight of water. So what it's saying is that 1 gallon of water weighs 8.34 pounds. Okay, so let's do some math. We are being asked to calculate the specific gravity for a solution that weighs 10.27 pounds per gallon. And we have a list of possible answers. A is 0.81, B is 1.23, C is 1.93, and D is 18.61. So remember, specific gravity is unitless. So these are just numbers. Okay, we also have our specific gravity equation, which this equation is provided on the WPI formula sheet when you take your exam. So you don't have to have this one memorized. All right, let's see what our solution is. First, we are going to figure out what we're trying to calculate, and in this case, it's specific gravity. Okay, Next, we want to know what the equation is telling us, what information we're given. So we're told that our solution weighs 10.2 pounds per gallon. And because it's pounds per gallon, we know that that is a specific weight. So let's move to step one. Step one, again, is setting up the equation to solve for the unknown, specific gravity. Well, the equation is already set up to calculate specific gravity, so we don't have to rearrange it. We can move on to step two. For step two, we're making sure that our units match. So specific weight is in pounds per gallon, and the specific weight that we're given is in pounds per gallon. So the units match. We can move on to step three. For step three, we want to plug in the value for specific weight and solve. So we have that specific gravity is equal to 10.27 pounds per gallon divided by 8.34 pounds per gallon. Those units are going to cancel each other out, and we're going to get an answer of 1.23. So 1.23 is the specific gravity of a solution that weighs 10.27 pounds per gallon. So our answer is going to be B. And what that means is that our solution is 1.23 times heavier than the weight of water. All right. Let's do another problem. So this problem tells us that a 12.5% chlorine solution has a specific gravity of 1.20. How many pounds would 55 gallons of this solution weigh? So what are we trying to figure out? We're trying to figure out how many pounds 55 gallons of the solution weighs. All right. And information that we're given, we are told that the specific gravity is 1.20. We're also told that the volume of our solution is 55 gallons. So step one, let's set up the equation to solve for our unknown. In this case, it's specific weight, not specific gravity. So we are going to have to rearrange our equation. So what we're going to want to do to isolate specific weight is multiply both sides by 8.34 pounds per gallon. So the 8.34 pounds per gallon cancel each other out on the right side of the equation. And we're left with specific weight equals specific gravity times 8.34 pounds per gallon. For step two, we're going to make sure that our units match. So specific gravity is a unitless number, and the specific gravity we're given is unitless. So we can move on to step three. So we're going to plug in the value for specific gravity and solve. So the specific weight equals 1.20 times 8.34 pounds per gallon. And we get an answer of 10.0 pounds per gallon. So is this our answer? Well, if you look, our answer is pounds per gallon because we just calculated the specific weight, right? But were we asked to calculate the specific weight of our solution? No, we were asked to calculate how many pounds 55 gallons of our solution weighs, not how many pounds 1 gallon of our solution weighs. So we have to do another step. In order to figure out how much 55 gallons of our solution weighs, we're going to multiply the specific weight that we just calculated by the volume of the solution. So to get the weight of the 55 gallons, we're going to take that 10.0 pounds per gallon that we just calculated, and we're going to multiply it by 55 gallons. The gallons are going to cancel each other out, and we get an answer of 550 pounds. So our answer is in pounds, and we were asked to calculate pounds. So 550 pounds is the weight of 55 gallons of 12.5% chlorine solution. All right, does anybody have any questions about that? Okay, so we're going to do a similar problem. We're told that the 50% sodium hypochlorite solution you use to increase pH has a specific gravity of 1.50 at 20 degrees Celsius. How many pounds would 20 gallons of this solution weigh? And so again, we have the specific gravity equation, And we have a list of answers. A is 3.6 pounds per gallon. B is 197 or 3.6 pounds. B is 197 pounds. C is 250 pounds. And D is 550 pounds. So the first thing we want to do is figure out what we're trying to calculate. And again, this is how many pounds our solution weighs. We're told that the specific gravity is 1.50 at 20 degrees Celsius. And the volume of our solution is 20 gallons. Okay, so step one, again, we're going to set up the equation to solve for the unknown, which in this case is specific weight. So like last time, we want to multiply both sides by 8.34 pounds per gallon, and that's going to give us an equation that says specific weight is equal to specific gravity times 8.34 pounds per gallon. For step two, we want to make sure that our units match. Specific gravity is unitless, and so we are good to go. We can plug in the value for specific gravity and solve for specific weight. So specific weight equals 1.50 times 8.34 pounds per gallon. And we get a solution of 12.5 pounds per gallon. Now again, we just calculated how many pounds 1 gallon of our solution weighs, but we want to know how many pounds 20 gallons weighs. So we're going to calculate the weight of the 20 gallons of the solution by taking the equation we just did, and we calculated the specific weight. And so we're going to multiply that by the volume of our solution. So the weight of 20 gallons of sodium hypochlorite equals 12.5 pounds per gallon times 20 gallons. The gallons cancel each other out, and we get 250 pounds. So 250 pounds is the weight of 20 gallons of 50% sodium hypochlorite solution. And our answer is C. Does anybody have any questions? Okay, let's do one more related to specific gravity, and then we're going to move on. So we're told in this problem that the sodium hypochlorite in your tank, in your day tank, is getting a bit old, and you want to determine its percent concentration. So you weigh a gallon of the solution, and your scale reads 9.08 pounds. So what is your percent concentration? All right, well, this is a little different because we're being asked to calculate percent concentration. And so far, we've been working with specific gravity. Right? We're told that the solution has a specific weight of 9.08 pounds per gallon. So we took out a gallon and we weighed it. And so we have that specific weight. Well, we're also given this table. And this table is the percent concentration, how it relates to specific gravity. So we can get the percent concentration if we know our specific gravity. So we're going to use our specific gravity equation. The first thing that we're going to want to do is set up the equation to solve for our unknown, which in this case is specific gravity. And that's how the equation's already set up. So we can move on to step two. We want to make sure that the units match. We're given the specific weight in pounds per gallon, and that's what the specific weight is in our equation. So let's move to step three. We're going to plug in the value for specific weight, and we're going to solve. So specific gravity equals 9.08 pounds per gallon divided by 8.34 pounds per gallon. So the units cancel each other out, and we're given, or we come up with an answer of 1.09. So for step four, we are going to want to use that specific gravity that we just calculated to determine the percent concentration using the chart. So 1.09 isn't on the chart for specific gravity, but we do have 1.08, which is, or 1.089, which is pretty close. So we can round, and our percent concentration then is about 6. So we have a percent concentration of sodium hypochlorite of about 6%. Okay. Now, You can do this again by calculating specific gravity, or if you have a hydrometer, you can skip that step of calculating the specific gravity, and you could use your hydrometer to measure the specific gravity of your solution. And then you would take the number that you get from your hydrometer, and you use that to read your chart. Okay, so that's another way to do it without having to calculate specific gravity. Or if you're really into math and you like playing around with instruments, you could find the specific gravity both ways. You could calculate it using the equation, and you could measure it using the hydrometer. And so that might be a really good way to check your math and to see if your hydrometer is calibrated. All right, does anybody have any questions about specific gravity before we move on? Okay, so we're going to move on to our last topic of the day, which is feed rate. And so there are different types of chlorine products that we can use to disinfect, and each have their own purities. So being able to calculate the proper feed rate for our system is really going to help us to ensure that we're adding the correct amount of chlorine to our system to achieve the dosage we need to properly disinfect, regardless of what kind of chlorine we're using. I'm not going to go into too much detail here, but there are 3 types of chlorine. We have gas chlorine, which has a purity of 100%. We also have solid chlorine, also known as calcium hypochlorite, and this has a purity of 60 to 65%. And we also have liquid chlorine, or sodium hypochlorite, which has a purity of 10 to 12%. So how does this relate back to the solids concentration and the chemical solutions that we talked about before at the beginning? A chemical solution with 1% purity is equal to 10,000 milligrams per liter, which is the same as 10,000 parts per million, if you remember. So there are a number of situations in a water system where the feed rate formula comes in handy when using chlorine. So we can use it when we're disinfecting our drinking water just on a day-to-day basis. This can tell us how much chlorine we need to be adding daily. We can use it for shocking wells if we have to disinfect. So let's say you've had some E. coli hits in your well and you need to shock your well. So you can use this feed rate formula to figure out how much chlorine you need. If you want to batch chlorinate your stored water like you would in a clear well. You could also use it to know how to proactively shock your distribution lines to prevent contamination if you've had to do any repairs on your line or if you've had any new construction on your lines. So feed rate is the amount of chemical in pounds or gallons that you feed into a volume of water over a period of time. And it's expressed in units of either pounds per day or gallons per day. So this is the feed rate equation that you're given on the WPI formula sheet. So let's just take a minute to look at it and see what the different components are. So feed rate is in pounds per day, and it is equal to dosage in milligrams per liter. So as we talked about, dosage is the amount of chemical solution that's fed into a volume of water. We multiply that by flow. So flow is the volume of water in millions of gallons per day that you're feeding into the chemicals into. And you multiply that by 8.34 pounds per gallon. So do you remember what that number is? That's the specific weight of water. So this converts the volume we get from our flow in million gallons per day into pounds. Now, if you know the specific weight of your solution, you could use that number here instead. But otherwise, we're going to be using the specific weight of water. So we take all that and we divide it by purity % expressed as a decimal, which is the purity of the chemical that you're feeding into the water expressed as a decimal. So how do we express a percentage as a decimal? Well, you take your percent and you divide it by 100%. So if our chemical solution has a 65% purity, what is that as a decimal? Well, it's 65% divided by 100%, and we get 0.65. All right, so if you use liquid chlorine, you probably don't want to know how many pounds per day you need to add to your system, right? You're probably more interested in how many gallons per day. So this feed rate equation is in the units of pounds per day. So I'm just going to show you how to convert this into gallons per day. So the first thing that we can see here is that we're getting pounds from the specific weight of water. And as I mentioned, this factor is here to convert our units from gallons to pounds. So if we want gallons instead of pounds, we can just get rid of that number. And what we get is we get a feed rate in gallons per day is equal to dosage in milligrams per liter times flow in million gallons per day divided by purity percentage expressed as a decimal. Now, if you forget how to kind of convert this equation into gallons and you use the feed rate in pounds per day, that's okay. You can do all the math, and then what you're going to want to do at the end is divide your final answer by 8.34 pounds per gallon, and that'll get you gallons there in the end. So you could either drop that number at the, before you do all your math, or you can, cancel it out at the end. Either way works. So what if you don't want rate? What if you just want to add chlorine once? Like if you have a tank filled with water and you want to put chlorine in that. So let's look at how to get rid of our rate or our time component in our equation. So our answer is in pounds per day, and we want to get rid of that day. So we're actually getting that time component in our solution from our flow. Now, like I had said, flow is equal to volume in millions of gallons divided by time in days. So if we want to get rid of days in our answer, we just want to get rid of the time, the day component in our flow. Well, if we do that, it's not a flow rate anymore, right? It's just volume. So we can replace that flow portion of the equation with volume in millions of gallons. So then what we would get is feed in pounds equals dosage in milligrams per liter times volume in millions of gallons times 8.34 pounds per gallon divided by purity percent expressed as a decimal. Okay, so finally, let's look at how we could get feed in gallons instead of pounds. So again, we want to get rid of that time component. Our answer is in pounds per day, so we want to get rid of the days. We know that the time component comes from flow, so we could get rid of that time component, and flow becomes volume. Now we want to convert the pounds in our answer to gallons. And if you remember how we did that, we just get rid of this parameter. So we could just cross that off. And what we get is feed in gallons equals the dosage in milligrams per liter times volume in millions of gallons divided by purity percent expressed as a decimal. Okay, is anybody having questions about that? Okay, so this equation can also be expressed as a pie wheel formula. And these are on formula, the formula sheets on your WPI exam. So I just want you to be familiar with these. If you've never seen them before, I just want you to know what the different parts are. So the top half of the wheel is one side of the equation. The bottom half of the wheel is the other side. And so what we're trying to do is balance the top of the wheel to the bottom of the wheel. And as with all of our formulas, you need to make sure that your units match the units in the pie wheel. You also want to note that this formula is for chemical solutions with 100% purity. So you're not going to be able to use pie wheel formulas if you're using liquid chlorine or if you're using solid chlorine. It only works for gas. Okay, so let's move on to the math. Let's do an equation. We are asked how many pounds of 60% calcium hypochlorite is needed to add to a system each day that has a flow rate of 1.5 million gallons per day to achieve a dosage of 1.1 milligrams per liter. Okay, so what are we trying to calculate? We are trying to calculate how many pounds of our solution we need to add each day. So we know that that is a flow rate or a feed rate. What do we know? We know that the purity of our solution is 60%. We also know that we have a flow rate of 1.5 million gallons per day and a dosage of 1.1 milligrams per liter. So the first thing we're going to do is set up the equation to isolate the unknown. So again, we're trying to figure out our feed rate. The equation is already set up for feed rate. So we can move to step 2. For step 2, we want to make sure that the units match. So dosage is in milligrams per liter, and we're given dosage in milligrams per liter. Flow is in million gallons per day, and our flow rate is in million gallons per day. Well, we need purity percent expressed as a decimal, but we have purity expressed as a percentage. So we're going to need to convert that into a decimal. So what do we need to do? Well, we want to divide 60% by 100%. The percentages cancel out, and we get 0.60. So now we have our purity percent expressed as a decimal. So we can move on to step 3. We want to plug in our values for dosage, flow, and purity, and then we can solve for feed rate. So our feed rate in pounds per day equals 1.1 milligrams per liter times 1.5 million gallons per day times 8.34 pounds per gallon divided by 0.60. And we get an answer of 22.9 pounds per day. So 22.9 pounds of calcium hypochlorite must be added to the system each day to achieve a dosage of 1.1 milligrams per liter. So that's what we figured out. All right, so does that make sense? Or is there anything confusing about that? Well, I think it's a little confusing. How do those units cancel each other out to give us pounds per day? So I just want to take a closer look of what actually happens to the units in this formula. Okay, so this is the equation that we just calculated. We found that 1.1 milligrams per liter times 1.5 million gallons per day times 8.34 pounds per gallon divided by 0.60 equals 22.9 pounds per day. Okay, so I'm going to write this equation out a different way. So this is the same thing, just written differently. Now, before we move on, what's something that we remember about milligrams per liter? How else can we write that? Well, if you remember from the beginning of the presentation, milligrams per liter can also be written as parts per million, which means that we can cross off the milligrams per liter units in this portion of the equation and replace it with million. So what we're saying is that we have 1.1 parts per million. Okay, so there are 2 ways to kind of move through this to show you how the units work out. And both are valid. And it depends on if you're more of a word person or if you're more of a number person. So we'll start with words first. This is the same equation, but instead of expressing it the way I did, I actually wrote out millions. So we have 1.1 divided by a million times 1.5 million gallons per day times 8.34 pounds per gallon times 1 over 0.60. So those millions are going to cancel each other out. and the gallons are going to cancel each other out, and we're left with pounds per day, which is the units of our answer. Okay. Now, if you prefer to work with numbers and not with words, we can write it out this way. So I'm just going to write out the number million instead of using the word. So we have 1.1 divided by 1 million times our flow, which is 1.5 times a million gallons per day times 8.34 pounds per gallon times 1 over 0.60. So those millions cancel each other out. The gallons cancel each other out, and we're left with pounds per day. Okay, so you don't have to do this whole process every time you want to calculate feed rate. I just wanted you to see how those units work, because I know the first time I looked at that equation, I was like, I don't really understand how that works. So now that you've seen me go through the math longhand, from here on out, you can just plug and chug numbers into this equation and just rest assured that, it works out. All right, so let's move on and do another equation. So we are told that a 500,000 gallon per day system has switched from gas disinfection to disinfection with a 10% sodium hypochlorite solution. How many gallons per day of 10% sodium hypochlorite are required to treat the water to a dosage of 2.8 milligrams per liter? Okay, and we have our feed rate equation. Well, what are we trying to calculate? We're trying to calculate how many gallons per day. And so that is our feed rate. We are told that we have a flow of 500,000 gallons per day with a purity of 10% and a dosage of 2.8 milligrams per liter. All right, so for our first step, we are going to rewrite the equation to solve for feed in gallons per day, because our feed rate is currently set up to calculate pounds per day. So we have those pounds, we want to replace it with gallons, and if you remember from before, the easiest way to go about doing that is to just get rid of the specific weight of water in the equation. So what we get is feed rate in gallons per day equals dosage in milligrams per liter times flow in million gallons per day divided by purity expressed as a decimal. Okay, so we want our feed rate in gallons per day, and now we have our feed rate in gallons per day. So we could move on, as how I've replaced the equation here. So we can move on to step 2 and make sure that our units match. All right, we're given dosage. We want dosage in milligrams per liter, and we're given dosage in milligrams per liter. Okay, well, we need flow in million gallons per day, but we were given flow in gallons per day. So we're going to need to convert that to the correct units. And so the way we're going to do that is we're going to divide 500,000 gallons per day by 1 million, and that will give us 0.5 million gallons per day. Okay, so now our units for flow match. And now we want purity, but again, expressed as a decimal. So we're going to take that 10% and divide it by 100%. Units cancel out, and we're going to get 0.10. So now purity, the units for purity match, or purity is expressed correctly. We now want to plug in the values for dosage, flow, and purity and solve for feed rate. So feed rate in gallons per day equals 2.8 milligrams per liter times 0.5 million gallons per day divided by 0.10. We get an answer of 14.00 gallons per day. So what that is saying is 14.00 gallons per day of 10% sodium hypochlorite are required to treat 500,000 gallons of water per day to a chlorine dosage of 2.8 milligrams per liter. All right, does anybody have any questions about how we solve that? Okay, We are cruising along. We have one more problem to go through. All right, so we are told, or we are asked, how many gallons of 10% sodium hypochlorite are required to disinfect the water in a 20-foot diameter tank with 30 feet of water to a dosage of 5.0 milligrams per liter. Okay, so what are we trying to calculate? We're trying to calculate how many gallons of our solution is needed to disinfect our tank of water. Well, this isn't a rate, right? We just need to do it once. So we want to change our equation from a feed rate to just a rate, or just feed rather. Right, so we are going to take the days off of our flow, which you remember then turns that into volume. Okay, and then the next thing we want to do is get rid of the pounds in the, get rid of the pounds in the answer and convert it to gallons. And so we do that by getting rid of the 8.34 pounds per gallon number in our equation. So I'm going to rewrite the equation to solve for feed in gallons. So after all of that manipulation, we get feed in gallons is equal to dosage in milligrams per liter times volume in millions of gallons divided by purity percent expressed as a decimal. Okay, so that is the equation that we're now going to work with. Let's see what information we're given. We're told that we have a 10% sodium hypochlorite solution, so the purity then is 10%. We're also told that we have a dosage of 5.0 milligrams per liter. Well, we need volume in order to calculate this, but we're not told the volume of our water. But we are given the dimensions of our water, right? We're told that it's in a tank with a diameter of 20 feet and that the water is at a height of 30 feet. Okay, so for our next step, we need to calculate the volume of our water, and we want that in millions of gallons. So we're going to need to figure out the volume of a cylinder because that's the shape of the water. In order to find the volume of our water in millions of gallons, you have two options. So you have the volume of a cylinder equals pi r squared times height, or the volume of a cylinder is equal to 0.785, which is half of pi, times the diameter squared times height. So I'm going to use the pi r squared to calculate our volume. So for step 2, again, we want the volume of our water. We're told that the tank diameter is 20 feet. Well, we need radius, not feet. So if you remember, radius is half the diameter of the tank. Radius is half of the diameter. So we are going to take our diameter of 20 feet and divide it by 2, which gives us a tank radius of 10 feet. And we're also told that the water height is 30 feet. Okay, so we're going to set up our volume of the cylinder equation to solve for the unknown, which is the volume of the cylinder or the volume of our water. They're the same thing in this case, right? So the equation is already set up that way. So we're going to move on to the next step and make sure that the units match. So in this case, it says on the equation that the units must be compatible. So they have to be the same units as each other. Well, we have tank radius in feet and we have the water height in feet. So the units do match each other. So we could move on to step 5. We're going to plug in values for radius and height, and we're going to solve for the volume of water. So the volume of our water is going to be pi times the radius squared, which is 10 feet squared, times height, which is 30 feet. And we're going to get an answer of 9,425 cubic feet. Well, we don't want our answer in cubic feet, right? We want our answer in millions of gallons. So we are going to have to convert cubic feet to gallons first. So in order to get that, we have the volume of water in gallons equals 9,425 cubic feet times 7.48 gallons divided by 1 cubic foot. Now, this is a conversion that is available on the WPI formula sheet, so you don't have to have that memorized. The cubic feet cancel each other out, and we get 70,500 gallons. All right, well, we're not done yet. So for step 7, we need to convert gallons to millions of gallons. So we take the volume of our well, and we get 70,500 gallons times 1 million gallons per 1 million gallons. That was a little confusing the way I said that, but the gallons cancel each other out, and we get 0.075 million gallons. Okay, so now we can go back to our original question, and we now have the volume of water. So we have our formulas set, or our equation set up correctly. Next, we want to make sure that the units match each other. We want dosage in milligrams per liter, and we're given dosage in milligrams per liter. We need volume in millions of gallons. We just calculated volume of our water in millions of gallons. We need purity expressed as a decimal, but we have it as a percentage. So we're just going to divide by 100%, and we get 0.10. So now we have our purity correct. So let's move on to step 9. We want to plug in our values for dosage, volume, and purity into the equation, and then solve for feed in gallons. So feed in gallons is equal to 5.0 milligrams per liter times 0.075 million gallons divided by 0.10. We get an answer of 3.75 gallons. So 3.75 gallons of 10% sodium hypochlorite are required to disinfect the tank to a chlorine dosage of 5.0 milligrams per liter. All right, so that was the last equation that I had for you. I hope that you try some of this math out on your own system. The key to getting good at it is just practice, practice, practice. So again, I encourage you to try to calculate these things for your system, and don't hesitate to reach out if you have any questions about math or you need help with anything.